All right, everyone. So this is chapter 9, the discussion on storage management before we move into our last chapter next week. So this chapter, we're going to discuss how the storage being managed within your system to better accommodate the performance of the operating systems. So especially when it comes to the managing storage, our main storage is the memory, how you better manage the memory. So we discuss about how we address the memory locations in our chapter 6 discussion with different indexing or addressing modes. But now, even with different addressing modes, how are we going to making it sure the organization of the memory is in a proper way to reduce the redundancy, reduce the fragmentation, reduce uh, delaying accessing certain memory. So in this chapter, it's present memory allocation techniques, 5 of those types: uni-programming, fixed partition, multi-programming, variable partitioning, multi-programming, and paging, alongside with virtual memory. And so some of those words are familiar to you and some may not. We'll go through briefly one by one. In uni-programming, the operating system reside at one end of the memory and the application at the other end. System only execute one job at a time. The best example will be your PEP 8 and PEP 9 architecture, uh, where you communicate with one program at a time. The operating system will accommodate one given program at a time, and as soon as that program terminates, you can flush entire memory and restart for the next program. So that sounds pretty easy because there's no much of a interaction between one program to another. Therefore, the fragmentation is very minimal. But sometimes we do like fixed partition multi-programming. In the same memory area, you accommodate location for different programs. How this gonna happen now? Operating system in one fixed reserved partition of memory, multiple processors in fixed partition of memory must solve the address problem. So you may have multiple operating system, multiple program running the same operating system, and the same time operating system will have its own addressing modes. So as I said, same program may use some of the operating system memory locations as well as the program operating systems. At the same time, another program may run on the same environment that use the same memory environment. So memory allocation for each operating process is within the same memory, but switch between accordingly. The next idea, the next concept is the logical addressing. Logical addressing is the addressing generated by the assembly, assuming the program beginning at address 0. So if you remember our previous example in chapter 6, you always start with the memory address 0. From there, you assign a address location for each one of those instructions. So our assumption is we always start from the address 0, and from there onwards, we assign memory locations. But keep in mind, this is only for PEP 9 architecture because we had a luxury of flushing our memory before we jump into a next or the new instruction. But if you have a multiple instruction run on the same memory, or I mean multiple processes run on the same memory, this starting at 0 location is not possible all the time, but you can have a logically defined 0, and from there you can define where my next instruction is. You have a logically defined relative address, memory address 0. Okay, now in this logical addressing mode, so you have your logically assigned address, which is going to map to your physical address. So you request for the logical address starting from the base register, uh, and from there you have your physical address need to be obtained. If it is within the range that looking for, you return true and return it as a valid physical address from your memory. If it is not within the range, you may return false, which is an illegal address or address is not available, basically an interrupt. So now let's talk about a little bit on what problems that you may come up with fixed size fixed size partitioning. So when you go for a fixed size partitioning, if you have a smaller jobs that need or waiting for a memory space, scheduling a small job in a large partition gonna make a lot of space wasted. So therefore, the fixed size partitioning is not a most appropriate way to make things work. So alternative will be you have a variable size partitioning. So depend on the program, depend on the process, you have a different size of partition allocated for each each operating process. So establish partition only when the job is loaded into memory. The size of the partition can be matched the size of the job. Depend on the size of the job, which depend on the requirement, you change the size. So therefore you have a larger partition and you divide the size that allocate for each partition depend on the size. So job 1 needs size 12, job 2 needs size 8, job 3 needs size 12, job 4, 4, 5, 4, likewise. So therefore, to accommodate this, so you go in a sequence and go back to other job whenever those jobs need some attention. So you have a job 1 started, job 2 started next, 3 started, and some point job 1 has been stopped. So to show that in a different diagram as you see it here, so you have job 1, job 2, 3, 4, 5 scheduled one after another. When job 6 comes into the play, job 1 is already completed. Job 1 is already completed. So therefore, yes, you may place job 6 where it is, as at the time that job 6 is coming into the queue, job 1 is not completed. Rather, both job 1 got completed and job 6 arrive on the same time. That's why job 6 is queued here. But when job 7 comes in, job 5 is already completed and it is being placed right here at the top because there is a available memory from the job 1 completion. So therefore job 7 is sent to the topmost memory location. And the same way job 7 is there. Now, as your memory got shattered here, you see some fragmentations here. So there are alternatives. What we could do is we could switch, rather shift everything to the top to making it sure there's no memory gaps. Or else you can do the same by just shifting this J6 to here, right? Or one option will be switch everything to the top, or else you can just bring J6 here. So depend on the memory architecture, depend on how the memory being managed. So how they accommodate jobs can be varied. As you see it here now, job 1, 2, 3, 4, 5 in the queue, right? All 5 are in the queue. When job 6 arrives, it can be set to the topmost position. Therefore now 2, 3, and 4 still continue. Job 5 finish and 7 comes in and it is sent to the next available location, even though J2, J3, and J4 still in the queue. So as I said, problem with this variable type of partitioning is you will see some fragmentation. Consolidating whole is time consuming. So you have to have a mechanism to better accommodate this. So now we can move into the discussion on paging. paging is a different kind of approach rather than call it several small holes fit to the problem. Fragment that program fit in the holes. A job is divided into a pages. So you have your first allocated space for your job, then you divide it into a small pages. So main memory is divided into a frames, each one of the same size as a page. So to better explain that, I can say it like you make a smaller versions of main memory from your main memory. So you create a kind of a chunks, small frames. So frames are allocated for the memory to better expand it in the same size as a page. All the pages gonna be the same or the each are equivalent in size. So therefore, the no collisions hole will be ever required to accommodate when you have the paging as a option when you use memory allocations. What do you mean by that? So now you have your pages defined here. Each page is same in the size, and you have your main memory. So main memory is being divided into 1 kilobyte frames. So you have your job 2 here, right? In the page one, job 3 here in the page 2, job 1 here again at page 1, right? Likewise. So when you define the page, you also need to define how many frames you need in your page. So job 2 has a 0 frames, job 3 has a 2 frames, job 1 has a 3 frames at this location. Job 3 has a page 0 accessed here, which is a frame number in decimal is declared as 6. So likewise, each page of job 3 is connected to the job 3 frame area. So page 0, job 3, page 1, job 3, page 2, job 3, page 3, job 3. So now, as we divided our main memory into frames, so now we have to have a 2 addressing mode to show this situation. So you first have a logical address, what we call it, which is with a page number and the offset, and the physical address that is also with the frame number and the offset. Okay, if we move forward from there, so now as I said, so your logical address will have a page number and the offset, and the physical address will have the frame number and the offset. So logical address, the page number and the offset retain the same even at the physical address, but logical address will have the page number that's going to find where my page is from the page table, and mapping page number is directed to the physical address, where letting you to find the real physical address of the memory location that you're looking for. Basically, memory address the CPU is looking for. So CPU will not get the direct physical address, but it has to go through the page table to map the physical address. Then the offset will give it the final address. So some disadvantage of these are, we can call it as an internal fragmentation. Within a page, there can be some fragmentation that can happen. So even though that we try to minimize the fragmentation, but still there can be internal fragmentation that can arise. So to execute a program, the entire program must load it into a memory. Most large programs have many sections of code that never execute. Memory is used inefficiently, with parts of the program taking up main memories unnecessarily. Okay, virtual memory. So virtual memory is a extended way of addressing the memory issue whenever your memory is running out. So you need to find temporary memory which is not fast or efficient enough as your real main memory, but it is of course a larger than your physical memory. How we going to handle this? We're going to take some space from your hard disk and convert it into a um, dedicated memory area. So people who have installed Unix operating system know what I am talking about here. We call this memory area as swap memory in your Unix architecture. But in Windows, we do not manually assign the virtual memory, but Windows itself will take care of it to assign something about the double of the size of your physical memory as a virtual memory. So whenever we are running out of space in our main memory, so it will jump into a physical area from your hard disk and obtain some memory area to keep track of the paging. So as you see it here, your main memory to have memory allocated and your frames are in your table. So frames are loaded from the frame number, and frame numbers are coming from a two-page table, J1 and J2. Not only that, whenever you're missing some of this information, rather, I should not say missing, whenever you are in need of extra space to accommodate your paging area, you go to your hard disk to get that info. So within your memory, you have frames created. Now, even if you have frames are not gonna be enough, you may also jump into a uh, paging table that's come from your hard disk, which is we call as a virtual memory. So basic idea of the page table: one page table for each program, convert logical address into a physical address as in paging. Loaded bit is 1 if the page is in memory, if not otherwise. And frame table, one frame table with entry for each frame, dirty bit initialized to 0 when the page is first loaded into memory. So this is a special indicator, just like NVCZ indicator, the registry that we had in our von Neumann architecture. So you have additional bits created whether that page is in memory or not. So you will set it to 1 on store word to the frame, not on load word. So allocating a frames before a job start execution, how many frames should be allocated for the job is defined by the size of the job. So you need to have your memory, your processor need to have an understanding how much of a memory location that you need. Depend on that, the size of the frame allocated will be vary. So when you replace this, there are multiple ways to replace the page area. One obvious thought that would come to your mind will be first in goes out first, FIFO, or least recently used is goes out first. So any location that not been used recently will taken off from your memory, giving priority to more frequently used area. So in your page table, if you follow the first in first out architecture as you see it here, you have 6 comes in, so 6 goes down as the 8 comes in, both goes down as the 3 comes in. Now 6, 8, 3 are in here. So next request is for 8, all 3 are in. Next request is for 6, right? Or that is also in. And when you're looking for 0, 0 is not in your table. So now keep in mind, as you see the false dirty bit raised to F here, that is because when you're first looking for 6 and 8 and 3, none of those are in your table. But at this point, all 3 being loaded, when you look for 8 here, 8 is already in your table. So you don't need to call it false. When you call for the 6 second time, it is in. When you call for 0 now, 0 is not in there. So you need to replace something to accommodate 0. What we replace is the 6 because we follow the first in, first out algorithm. So then we looking for a 3. Yes, 3 is still in. When you're looking for a 6 one more time, now 6 is gone. We again raise a false command here. Replace 6 with last one, first in item, which is 8. And 3 again in. 5, we are looking for 5. 5 is not in. Raise the flag and insert 5. 3 again, raise the flag because 3 is gone right here. Insert 3 again. Now we're looking for 6 one more time. Yes, 6 is in. So if the size is a little larger, this can be a little different. As you see here, how many falls are here? 1, 2, 3, 4, 5, 6, 7. Here, 1, 2, 3, 4, 5, 6. So number of hits, number of misses can be a little less if you have a larger size, but that doesn't guarantee that all the time. In general, we can say the larger the number of frames allocated to a program, the fewer the number of faults that you may experience, but that's not the way to go always, because you don't need to allocate larger frames if you don't use all the frames very frequently. So few cases with FIFO and increase in the number of frames, increase the number of page faults. So number of frames increase, number of page faults decrease. How about the same thing with least recently used item being taken off when you have a new replacement? So first 3 times it's same, 683 comes in the same sequence. None of those are existing in our table, so that's why it's returned false. When you go for 8 next, 8 is in, no false. 6 in, no false. 0. So when you try to insert now 0, what was the one that used last was 3, because 6 and 8 are used previously. So 3 is being taken off and replaced with 0. So replace with 0. So next time we're looking for 3 now. Now 3 is gone. What has been used last is 8 now. So you take 8 out to accommodate 3. Then you come get 6. 6 is in, no false. 3 is in, no flag here. 5 is not there. So you need to take the last in out, or the least recently used one out, which is 0. 0 is taken off. 3 comes in, 3 is in, 6 comes in, 6 is in. Now you ended up having 6 flags when you use size 3 frame for your paging for LRU. Okay, so that's all about how you manage the paging. Now we'll jump into the discussion on the file management. So when it comes to the file management, the creating a file, how you delete it, how you rename it, how you open and edit it, how you read and next data item from the file. So this is what matters. So how you manage your memory to accommodate this. So probably you have familiar with this kind of a cylinder architecture from your basic computer science courses, how the hard disk been organized. So in a cylinder-like architecture, hard disk is divided into a space like this. We call these tracks and sectors. So you divide it into a tracks and sectors. As a result of tracks and sectors, you ended up having very small blocks, very small box. So therefore, if you're looking for something stored in this architecture, you need to send your read-write header that you have here to find where my block is, the block that I'm looking for that particular file is. So there will be certain delay if the block is in the other side of the disk. So 180-degree need to be turned to find that head, because the arm is steady, it doesn't move, head is steady, but the disk rotates. So that's why you will see your disk rotate very fast, generate a huge noise if you have a disk type hard disk in your PC. Your fans start rotating higher to cool it down. So there will be some seeking time for head to reach the cylinder, some latency, time for start of sector to rotate to a head, and transmission time from a sector to pass under the head. So as you have this architecture, if your item is somewhere here, so you need to wait till the signal is loaded and pointed to the disk, and from disk, how much of a time it takes to rotate it to a level that you want to access it. There are multiple ways that you allocate files: the contiguous, linked, and index. Each one of those has its own mechanism, own structure. If we move forward from these three different type of file allocation techniques, so contiguous, linked, and indexed. So contiguous allocation will specify where your file's starting location and how many more locations that you need to complete the file. So you have the start location and the size. So your start location is right here at the 5 from 6 location, 5, 6, 7, 8, 9, 10, which is 6 size, 6 space size of the file. Then your next file is a starting point at 18 with the size of 3, 18, 19, 20. So in your directory, so how the files been organized is in such a way you define the starting location and the size. That is contiguous allocation. Link allocation, all these three kinds are similar, has some differences. In the link allocation, you have the start location, just like the linked list architecture that we discussed in our 200 class. So each file space will have a link to a next location if it is linked to something else. If there's no link, that's it. If there's no link, that's it. So as you see it here, if you take an example as a 18 is the start location, 18 is linked to 19, and 19 is linked to 2, and from 2 it's end. That file ends right there. And if you check another file, you have a starting point at 5. You have starting point at 5, then it is linked to location 11. 11 is linked to 12. 12 is linked to 14. 14 is linked to 23, and 23 is linked to 20, and file terminates. See that? So linked kind of architecture. And the other option will be kind of a more of an index architecture. Like in an array, you keep the track of spaces that are allocated for a certain file. So you have a file, one file, the term paper is allocated with the memory location 5, 11, 12, 14, and 23, and 20. So it's kept in an index list. And the other file mailing list is 18, 19, 20, 18, 19, 2 rather. So that's another way. So those are the basic way of keeping track of your files in the file allocation tables. So if you remember the FAT formatting system, file allocation table. FAT stand for file allocation table. There are more than FAT in the file allocation tables. If you have seen NTFS or EXT, EXT4, EXT3, 2, 1, or some other type of architectures like swapping, a swap area, Samba, there are different way of file allocation in different operating system and different environment. So, but most of those use one out of these three given allocation structure. So rest of the chapter is not going to be questioned in your exam, but you better have a brief understanding how the errors being detected. If errors being occurred in the file allocation or memory allocation, but as it is not a part of your this course requirement, I'm not going to go through that part of the slides. So your expectation is to cover up to 9.1 to 9.3, where we cover the storage management for memory and storage management for file. So that's it for the day. We'll talk more when we meet live.